more precisely min cost perfect matching. I mean, this is something we will actually use when we look at approximation algorithms for TSP. So it's useful to know, and it's a nice combinatorial problem. It's the whole algorithm will be somewhat mysterious, but it will be much better understood when I do linear programming next. Okay, so we will do before and after, and so after doing LP, we'll also look at this algorithm again. Then you'll see a different perspective on the algorithm. So what is the okay? Let's just go back to the standard. We're talking about bipartite graph. UV are the two partitions. So we know how to do maximum matching. Maximum matching is the maximum number of collection of disjoint edges, and how did we do? Remember, we did using MaxFlow. Okay, so we set up a source sink and added a capacity of 1 for all edges, right? So we did this. So now it's useful to know how the algorithm works. So let's look at this simple network. So we created the source. Suppose this is my graph, right? What I have is this graph. Then we add these edges and we create this sink. Then you say run MaxFlow with all capacities 1. And whatever MaxFlow you get, we pull out a maximum matching out of it. Okay. Now, how does MaxFlow algorithm work? If I use the Ford-Fulkerson paradigm, we will send a flow. Let's say I send suppose I send a flow through this edge. Okay, a flow of 1 through that edge. Then you construct a residual graph, and then you try and look for what is a residual graph in this case. Your residual graph will have S to B1, B1 A2, and A1 B2 and B2 to T, right? Is that all? From A1 to S, more importantly from A2 to A1. That's what's going to be useful for us now, because if I do not have this edge, if I did not have this edge, right now there is no ST path at all, and you might just incorrectly conclude that you've got MaxFlow. But since I have this edge, now I have an ST path, which is that ST path. I'll go like this, then here, and then go back here, and here, and here. That's an ST path, and we augment the flow through that. But see, what's happening in that is that we pull out this edge. This was an edge in the matching, which we remove it now. It was an incorrect decision, so we remove it, and we are adding these two forward edges. Okay, so the maximum matching is actually these two edging. So I sent a flow through this edge, but that's removed now. You can think of it as now I am sending a flow of this and this. Okay, so basically I'm going to have these two edges in the matching. This flow is removed. So the flow that was coming out of S will actually go here and come here. The flow coming to B1 will go here and come to A. Okay, that's the final interpretation. Okay, so what we are doing is we start with some matching, maybe an empty matching, and then we got a matching of one edge. Now, what we are constructing is what is called an ST path in the matching literature is also called an augmenting path. So what is an augmenting path? So ignore this SB1H. It starts with an unsaturated vertex. So after this matching, A1 and A2 are saturated. They have a matching at both endpoints. So now this new augmenting path starts with an unsaturated vertex, okay, and it takes an edge. Clearly, it will be a non-matching edge. Why? Because it's unsaturated. There is no matching edge to it anyway. So it will take a non-matching edge. You follow a matching edge, and then a non-matching edge. Okay, so it's an alternating path, augmenting path or alternating path. So I start with somewhere a non-matching edge, and then I have a matching edge, and I have a non-matching edge. If I have such a path, clearly I can remove this and add these two edges in my matching, and I can increase the size of the matching. Right? So this is one popular way of finding maximum matching, and this is what is happening in the MaxFlow algorithm anyway, which is to find what is called an alternating path. So I start with some matching, then I find an alternating path which starts with an unsaturated vertex, non-matching, matching, non-matching. Okay. It might still go and say, okay, I have a matching. Finally, non-matching, and then a matching. But it ends with the non-matching. That means it has more non-matching edges than matching edges. Then I do a symmetric difference. What does symmetric difference means? That I take the edges which are not in the matching in the solution and remove those in the matching. Then I get strictly larger matching. Okay. So this is one way of augmenting the matching, and if I am looking for a maximum matching, I keep doing this, and when I can stop whenever there is no alternating path, and what I get is a maximum matching. Okay, that's exactly what's happening in the MaxFlow. MaxFlow is much more a general version of it because you have capacities and so on, but when you project it to capacities being 1 and find maximum matching, this ST augmenting paths eventually boil down to finding this such alternating paths and then increase the matching. Okay, so this is one view useful to know when we talk about maximum matching problem. So the simple Ford-Fulkerson algorithm gives you a running time of mn, but you can find do some parallel lot of augmenting paths at one point, and the best known currently has a running time of m root n for bipartite matching. Non-bipartite matching story is a lot more complicated, but that also has a running time of m root n. Okay. So the problem we're going to look at today is that now I have edges not only have, there are no capacities anyway, capacities are all 1, but there is a cost associated with every edge, and we could even assume that what you have is a complete bipartite graph. So the cost version has size of u equal to size of v, and we can even assume E is all edges between u and v, because I'll put a cost of infinity if the edge is not present, and I'm interested in a minimum cost. There is a cost associated from every edge to some positive real number. So since it's a complete bipartite graph, there is clearly a perfect matching. U is equal to v, so I can just match every vertex in u with some vertex in v, and I get a perfect matching. So among all perfect matching, I am interested in find a perfect matching with min cost. So this is also comes up in many realistic situations. You can think of this is as people and jobs, and you want to associate persons with jobs, but there is some cost associated with this assignment. and you want to minimize the cost. Okay. So now we want to modify this augmenting path approach to find this min cost perfect matching. So when I have, so the simple intuition which seems to work is that instead of finding some ST path in the residual network, so you can, right, you can define this residual network for every matching exactly like the way we have it for a flow residual network. So if you have a matching, so this is my matching, I will have a residual network which I will call okay, we could have a, S and T as well. So exactly like the way, so whenever I have an edge UV in the matching, I will have BU in the residual network, and whenever I have a non-matching edge, I will have XY like this in the residual network. Okay. Similarly with S and U. Now I'm going to put cos. I'm going to introduce cos. So there is now all the edges in the graph as well as in the residual network. So we will assume these costs are 0 and these costs are the costs in the graph. Okay. So in the residual network, exactly the same way I am going to associate a cost. So if xy is a non-edge, then whatever that cost is Cxy would be the cost of this edge. Here it will be minus Cuv because it's this edge. It's going in this direction. Okay. So now you are dealing with a graph where edges have costs. So in the same way, I will, when I construct the residual network, I will have costs on the edges. And this whole augmenting also works. We have, so if I have a matching M, and you have an augmenting path P, then the new matching would be M plus P, which is this means a symmetric difference, right? Is this clear? Let's look at this. So this is my M here is A1, A2, right? And my P here was S to B1 to A2 to A1 to B2 to T. Okay, so when I talk about matching, I ignore this S and T anyway. So then my new matching is the symmetric difference of all of this, which means that just delete those which are in both and keep the remaining. That's what it is, right? What is the edge which is in both? A1, A2 is in both, so that's deleted. So the new matching is B1, A2 and A1, B2, right? A1, B2 and B1, A2. So that's what it is. Right? That's exactly what the augmenting thing is, because it's the same. Anything which is in this, because we will go in the opposite direction in the augmenting path, so this edge will be removed, right? Even if you think in terms of the flow, what does that mean? There was some flow of one in this direction. Now if it is part of the augmenting path, it is in the opposite direction and the flow will be removed. So whatever is left is what the edges with the new flow. So B1, A2 and A2, B1. So that's exactly this new matching. Okay. And interestingly, this is also true the way I have defined now. Cost of the new matching is cost of M plus cost of P. Let's see why again, right? Cost of the new matching. I mean, this edge will have cost 0 anyway, these two edges, so ignore that. So now, cost of the new matching is cost of this edge, but A2, A1 will have a minus cost, the way I have defined it, right? This is minus of CUV. So if I take the edge A2, A1, that will cancel out with this. And so it's cost of this plus cost of this. Okay, so cost of M prime. So this, I mean, so what have I said so far? Nothing really new, except that now the same augmentation, everything can be looked at, and in terms of the cost as well. If you have a new matching, which is basically you augment the flow through this augmenting path, then the cost of the new matching is cost of the original matching plus cost of this path. Okay, so now back to our problem. We have a cost on the edges and we want to find among all perfect matching, find the one which is a minimum weight perfect matching. The simple intuition is, which seems to work, is that instead of augmenting path by any path you are matching, augmented by the shortest path, where here shortest mean that consider the costs on the edges. Okay. In fact, Edmonds-Karp's algorithm in the Ford-Fulkerson also said use the shortest path, but there was no capacity cost on the edges, it was the minimum number of edges on the path. But here I am going to include cost. So, first idea for min cost perfect matching is augment using min cost path among ST paths. Use the one which has the minimum cost in ST. Essentially, this is going to be our algorithm. Start with some zero matching or empty matching and keep augmenting using the min cost path. Except we need to take care of some details and argue correctness, running time and so on. One problem we have to deal with when we want to find shortest ST path in the residual graph is that now edge weights have negative, okay, because these costs are all negative. So I can't first of all apply something like Dijkstra's. That's okay, we can deal with negative cost weights, like you can apply Bellman-Ford. But another big problem is what if you have a negative weight cycle? If you have a negative weight cycle in the graph, then this min cost ST path itself doesn't have any meaning because I can run through the cycle and get shorter and shorter path. So that's the only thing we need to deal with, and then we'll be ready to design our algorithm and prove correctness in the running time. Okay, so dealing with negative weight cycle. So one way we will deal with is that somehow we will change our cost, or we'll augment in a way that change the cost slightly in a way that you never have negative weight cycle. But before that, let's prove this nice simple lemma. Let M be a a perfect matching. Then M is of min cost if and only if GM has no negative weight cycle. Okay, so first of all, if suppose you are working with perfect matching, so this augmentation is actually what it's doing is only increasing the size of the matching. Okay, the cost is something for us to deal with somehow, and we will somehow argue that I'm always working with min cost matching, that when I reach perfect matching, I'm having a min cost perfect matching. Okay, why? Because if you are dealing with perfect matching, if you have reached a perfect matching, then you cannot have an ST path at all in GM. Why? And increase the size of the matching. Okay, that's one argument. Yes, but the other argument is that any edge out of S is saturated. Right? You have a perfect matching means what? So this is my U and this is my V, and I have, I mean, how do I get a perfect matching? This guy, suppose it's like this, that means this would be a path. So this edge would be saturated. I mean, this capacity is 0 anyway, but sorry, capacity is 1. It's a cost which is 0. Capacities are 1. Capacities are always 1. So this, how do I get a flow of 1? This will be saturated. So there, all the edges would be saturated. So there won't be any outgoing edge from S in the residual network at all to find the path at all. Okay. But so what I'm saying is, so you can't augment the number of edges, but maybe you can still decrease the cost. You've got a perfect matching, but somehow you can decrease the cost. And what we are saying is you can decrease the cost if there is a negative weight cycle, and otherwise you've reached minimum weight matching. Oh my God. So just like I can augment the matching using a path, I can do it with using a cycle in the graph as well. Right. So forget S and T. Suppose there is a cycle in the graph. How will it look like? Right. I'll go here. Something like this. Okay. So I have a cycle. This is how a cycle in UV would look like. A directed cycle. Okay, because all edges are going from left to right. Now I take my, so let's call this cycle as C, and I look at M prime is M plus C. This also makes sense, right? All I'm saying is anything in the matching and in the cycle, delete them and keep the rest. So what I get is a new matching. Okay. And what is the cost of the matching? By this argument, cost of the new matching is cost of M plus cost of C. So if cost of C is negative, then cost of M prime is strictly less than cost of M. So you got a smaller cost matching if you have a negative weight cycle. What if the cycle does not touch the matching at all? That's okay. Then you just take it. Yeah, I mean this is clearly true. So I can always talk about matching plus symmetric difference of another set of edges, whatever the set of edges is, and which by definition which simply says that anything which is common to both, delete it, take the rest. Okay. One question is why would it be a matching? Every vertex will have degree exactly 1. Okay, I know I'm dealing with perfect matching. Okay, good. I think we're working with perfect matching. So if M is a perfect matching, and if there is a negative weight cycle, then I just look at the symmetric difference of M and C. Every vertex is saturated. Every vertex of U and every vertex of V is saturated because it's a perfect matching. So if you take the cycle and do the symmetric difference, it means take the edges in the cycle but not in the matching, and in the matching not in the cycle, take them and remove the remaining. What you get is a different matching, right? So for example, suppose this edge means matching. If I have that kind of a cycle, then I take 1, 2, these 3 edges, then that cost would be smaller than the cost of the original matching. Okay, and keep the remaining edges of the matching for the other vertices. So one direction is clear. So what I showed is that if you have a negative weight cycle in the graph, that cycle will not, in GM, right? Yeah, that cycle will not have anything about S or T because there's nothing coming out of S, nothing coming into T. It's a perfect matching anyway in the residual network. So that cycle will be something like this, and if I augment my matching with this cycle, I get a strictly smaller cost matching. So this won't be a min cost matching. So that's one direction. The other direction is suppose there is no negative weight cycle in the residual network. The M prime. The M prime or something. No, M prime will be perfect matching. We'll see what, because yeah, actually that is the point I did not emphasize clearly. Since it's a perfect matching, let's see how the cycle will look like, right? So your negative weight, suppose this is a cycle. Is it possible that no edge of this is in the matching? First of all, right? Suppose this is my cycle. Okay. Now you have your M touches A, B, C, and D, right? It's possible that some of these edges are in matching. So, I mean, is it possible that my M would be like this? and AD is maybe a matching edge, and maybe there is a CF. So it matches CF, A, B. Yeah. I mean, what would be the degree of a vertex in M prime? Okay. Okay. I'm okay. It's a negative weight cycle in GM. Okay, so it's important. In the residual network, the forward edges are matching edges, and the backward edges are matching edges, and the forward edges are non-matching edges. Okay, so that means any cycle would be an alternating cycle. I think that's important. Good. So suppose ABC, if you, this is your cycle. Suppose this is my cycle in GM. Then I know that this is not in the matching, and I know that this is in the matching, because that's how, I mean, how would I have an edge from B to C? In the graph, remember, all the edges are going in the forward direction. So why is there an edge B to C? Because CB was a matching edge, and CD is not in M, and this is in M. So this cycle would be an alternating cycle. So when you augment, and if you look at the degree of every vertex, in the edges of this cycle, there will be exactly, the degree will be exactly 1. One edge will go out and one edge will come in. Okay. Yeah, this is exactly what I wanted. I wanted an alternating cycle. How can I guarantee it? Because in the residual network, a cycle would be an alternating cycle in the original graph. It alternates between matching edge and non-matching edge. Okay, so what did I show? That if you have a negative weight cycle in the residual network, I can augment it and get a smaller cost matching. I want to show the converse, that suppose there is no negative weight cycle in GM, and I want to show that you've reached min cost matching, right? And there is no negative weight cycle in GM, and suppose M prime is a matching such that cost of M prime is strictly less than cost of M. I want to get a contradiction. Suppose there is a matching M prime. Now look at M symmetric difference M prime. In GM, in the residual network, look at this. How will it look like, right? I'm looking at those edges which are not in M and in common, so those are in M but not in M prime. They will look like, anything in M will look like this. Right? So suppose you have a vertex, anything which has in M but not in M prime, no. So what? Both are perfect matching. What happens if you just take two perfect matchings and look at their symmetric difference? Okay, let's see how it will look like. Two perfect matchings So here is one perfect matching, and here is another perfect matching. Then it will look like exactly like this, a cycle, right? Because I am throwing away edges which are common to both. So that means that it will, if you take this, suppose this is a matching which is in M but not in M prime, then to match this in M prime, there must be another edge which will be like this, which is not in M. And if you follow this, then the degree of every vertex in this symmetric difference would be exactly 2. There will be one matching incident on that vertex of M and another matching incident on that on M prime. Okay, and so if this is in M, or no, if this is not in M, then it will, this is in M prime. Let's say this is in M, this is M prime, and this is M prime. Then M prime edges which are not in M will be in the backward direction, right? Anything, no. So it will be in the forward direction in GM. Okay, and this is in M, so it will be whatever forward backward means. So I have to be careful here. So this is an M prime, so it will have this edge, and anything in M, I claim it will be like this. I mean, I want to say that this would actually be a collection of even cycles in GM. That's what I want to show. Okay, I mean, what do you mean by collection of even cycles? In the undirected sense, forget the direction. In the undirected sense, every vertex has even degree, so it will be a collection of even cycles, because basically it's a two regular graph, so it will be collection of even cycles, M plus M prime. Okay, and what would it be? Its cost. This cost of this in GM would be that any edge of M would be in the backward direction, any edge of M prime would be in the forward direction. So it will be cost of M prime minus cost of M. Okay, so first what I am saying, if you look at the symmetric difference of M and M prime, every vertex has degree 2, so it's a two regular graph in the bipartite graph. So if you look at it in GM and look at its cost, the cost would be, because any edge of M prime in GM would be in the forward direction and any edge of M would be in the backward direction. So that will have a negative cost. It's exactly this. And since cost of M prime is strictly less than cost of M, this will be less than 0. What does that mean? That at least one of these cycles will have cost less than 0. It's a collection of even cycles whose total cost is less than 0.
As we assume that there is no negative weight cycle, so that cycle, cost of that cycle should be greater than 0. So C of M dash greater than Cm. What we assume?
Yeah, greater than or equal to Cm.
Greater than or equal to Cm. What we assume
is wrong. Yes. So either we can do it this way, or I mean, forget this assumption. Suppose you have an M is a matching and M prime is a smaller cost matching, then I will produce you a negative weight cycle. Okay, so now what's my algorithm? I'm going to start with zero matching and always ensure somehow that my residual network will have no negative weight cycle. Keep augmenting the edges. The augmentation just increases the size of the edge, right, by 1. So finally, when I reach perfect matching, since I have always ensured that there is no negative weight cycle, what I will have is a min cost perfect matching. Okay. So now I still haven't answered this question. Yeah, okay, now I have answered. How do I ensure that I will have no negative weight cycles at all? I haven't told you how to do that. So that's the next part, and then we'll be ready. Okay, so now for this we will introduce some cost on the vertices. Okay, so what is my goal now? Yes, start with some matching and augment, find an shortest path augmenting path. Keep doing this, but the augmentation happens by only and increases the edge by 1 every time. Finally, I'll reach a perfect matching. But somehow, the shortest path augmentation, I will argue that it ensures that we don't have a negative edge cycle when I start with, and the shortest path augmentation ensures that there is no negative edge cycle as we move on. So when we reach, we have a perfect matching with no negative edge cycle. So it is of min cost. Okay, so now so this is the part where actually if you look at it in LP and duality, you will be able to follow better, and we will see this perspective next time. But let's talk about this. So what I'm going to do is so we will have a variable, a cost PV for every vertex. When you look at an LP, it will be a dual variable actually. So in other words, if you think of this as people and this is jobs, and the cost xy is the cost of assigning person x to the job y. Okay, that is the cost. Now I'm going to give some signing bonus if I assign x to y to x. So px is some extra cost I'm going to assign to when I cost to x, and p of y is some reward of getting job y done. So which means that I'm going to talk about a new cost on the edge xy. What is the new cost on the reduced cost on the edge xy is that px, because there is some signing bonus I'm going to give it to x, plus there is a cost comes with the input graph, minus I get some reward of job getting done. So which I call this as a reduced cost on the edge xy. So now we will assign p values so that the following happens. following three conditions. They are all non-negative. For all x, y in the matching, okay, for all x, y in the graph, px plus cost of xy minus py is reduced cost is always greater than or equal to 0. And for all xy in the matching, px plus cost of xy minus py is equal to 0. Meaning that I have assigned x to y means that even after giving the signing bonus and the cost of the salary to him, x to y, and the reward I get, the net cost is 0. More importantly, anything which is not in the matching, the net cost is greater than or equal to 0. That's why I have not matched it. Here I have matched it because at least I break even here. So we'll ensure this for every, the P and M are compatible if the following happens. So this depends on the M, right? Which means what this condition says that the reduced cost is always greater than or equal to 0 because of B for any h. So now we will work with this new cost in the residual network. Because its costs are all greater than or equal to 0, there won't be any negative weight cycle, we will see, and you can apply Dijkstra and find the shortest path and keep going. Okay. Okay, so this is all mystery. Hopefully will be revealed next time when we do LP duality and stuff. But for now, let's just go through the motion. Let's look at negative weight cycle in GM in the original cost. Suppose C is a cycle in GM, okay, not containing SRT. Then cost of the cycle in the original thing is also the same as this is the using the reduced cost. You agree? So I have a cycle, okay, in the graph. I add the cost of the edges here. I have two choices. One, I look at the original cost on these edges, right? Of course, this will have a negative and so on. Take the original cost. Or I look at the reduced cost. What is this reduced cost? Which simply takes, it adds this vertex p value and subtracts this value, this vertex p value and adds the edge. Okay. Now I take the reduced cost of each of these edges and add them all. Both the costs are same. Do you see that? Why?
Adding px and we are subtracting when the
So the p's will cancel out. The p's will cancel out. Okay. Right? Because if I add A, B, C, then I will have PA plus CAB minus PB plus PB plus cost of BC, whatever that cost is, plus or minus whatever, minus BC and so on. So this PB cancels out, and since it's a cycle, it will come full circle, and it is all the P's will cancel out. It's the sum of the original costs anyway, right? So if I assign values to P values so that these conditions are met, then I will not have a negative age cycle in the graph at all, because this is greater than or equal to 0. If you add the reduced cost on every edge, because I am maintaining this property, the reduced cost of every edge in the residual network. So how do I assign it is something that I need to worry about. So now all I am saying is, to deal with negative cost, here is a simple shift. What we do is we change the cost a little bit, so that now the new cost of every edge is greater than or equal to 0, but the sum of the new cost is the same of the sum of the old cost. And so since this cost of the cycle is greater than or equal to 0, I will not have a negative age cycle as long as I ensure these conditions on P. When I augment my matching, I still have to make sure that these conditions are satisfied. If I keep maintaining things this way, then I will not have a negative age cycle. So now my algorithm is clear. Modulo the description of how I update P. How I update M is clear. I find an augmenting path, shortest min cost path in the residual network. Augmenting M, I can find any path, but I use the min cost path to update P values. That helps me to update the P values, and the size of M increases by 1 all the time, and I always ensure this P and M have this relationship so that there is no negative age cycle, and when I reach perfect matching, I can stop, because I have got a perfect matching where there is no negative age cycle in the residual network. So by the lemma we saw, we got a min cost perfect matching. Okay. So now I have to just tell you how to update P value, and then the algorithm is clear. And I have to tell you how do I start, right? So let's start about starting M and P. What are the values? M is equal to empty. I'm going to start with empty matching. But let's make sure, how do I assign P values, right? And we will assign P of x is equal to 0 for all x in U. For x in V, I have to be careful. For every x in U, I have ensured this. So that means even in this kind of edges, this PS is also 0. I think you can say that. So for every xy, cost of this is 0 anyway. Capacity is 1, but the cost is 0. So 0 plus 0 minus 0 is greater than or equal to 0. That's all ensured. M is empty anyway, so I don't even have to worry about this. But now let's see, how do I assign Py? What does this mean? That y has a lot of edges coming in, right? This condition tells me that for every edge, P of x, which is all 0 anyway, I have assigned them, plus the cost of that edge is greater than or equal to P of y. So that means P of y is less than or equal to cost of xy. So I could assign 0 as well for y. I think that's fine. Assuming the costs are all non-negative, I could assign for every y 0 and it will still satisfy. I could also do the following. I pick the min of cxy xy is a mean. But if cxy's are all greater than or equal to 0, then I could also assume it's 0. Yeah, so cos 0 would also work. So this is how I start. So my P and M satisfies those conditions. Then compute GM. I can compute the residual network for M with the costs. Find min cost, okay, GM and the reduced cost. Because these reduced costs are all greater than or equal to 0, so I can simply apply Dijkstra's. Find min cost ST path in GM and augment M by the path to get M prime while there exists an ST path. So the only part I need to now tell you is how do I get P prime so that these conditions are satisfied. Okay. Otherwise, algorithm is done. Right. I start with an empty matching. I mean, the reason this PEC plays a role is that I ensure that I have no negative weight cycle in the residual graph. If my P and M satisfies this condition, then I find the shortest path in the shortest cost path in the residual network. Then I augment, so increase the number of edges by 1 every time. In about n loops, I will have a perfect matching, and I always ensure there is no negative weight cycle by this property of P, and because of the lemma we proved, when I reach perfect matching, I have got a min cost perfect matching. I just have to tell you now how do I update P so that those conditions are satisfied. Now then, that ensures that there is no negative weight cycle. It turns out the following simple update does the job for me. Let P prime of V is equal to P of V plus length of the shortest path from S to V in GM. If I just do this for every vertex, I will now argue that all these conditions are satisfied for the new matching, right? To satisfy it for M anyway. Now P prime and M prime, they are compatible under these conditions, and then no negative weight cycle. You got one extra edge, keep going. So every time I am increasing the size of the matching, maintaining there is no negative weight cycle in the residual network. So when I stop, there is no ST path. I've got perfect matching with min cost. So I have to now show that these conditions are satisfied for P prime and M prime. Okay, so now Is it clear that the first condition is satisfied? It's if the shortest path's lengths are non-negative, then yes. Maybe I don't even need this condition. Okay, so we'll see this. 3 cases: xy is in M, xy is in M prime, and xy or M prime minus M, and x prime the remaining edges. I want to make sure that if it is an M, what happens? If it was an M prime but not in M, and if it was an M union M prime, what happens to these conditions is what I want to find out. Okay, case 1. Okay, so suppose xy is in M. Then let's look at the residual network. The only edge coming into X would be from Y. Right? To X, what are all the edges to X? From S, there will be an edge, but that will be saturated anyway, so that won't be there because xy is in M. In the residual network, there will be an edge from Y to X, and nobody else will come, to X because all the edges are forward. Anything in matching, it's only this would be there, right? So now in the shortest path augmentation, the distance from S to X would be equal to distance from S to Y plus 1 because of this only edge present. Okay. So, which means that P prime X is equal to I'm just adding P of X both sides. I added P of X to both sides. dsx plus px by definition is P prime X, and this is what I have. Now, so since this was in the matching, I know that this condition was true. For every edge in the matching, px plus cxy is equal to py. Okay, so let me also add p prime x plus cxy. Px plus cxy is nothing but py. Sorry, y plus 1. We are talking about the shortest path. This is clearly minus cxy. Right? We are talking about the length of the shortest path from S to X, where when I say shortest, I am talking about the costs on the edges. So the length of the shortest path from S to X is length of the shortest path from S to Y plus cost of this edge, which from my definition is minus cost of xy. Right? So what did I do? P prime x is I added px minus cxy. Now so I add now cxy because I really want to understand. Do I really want to? What do I want to understand? Yes, p prime x plus cxy is dsy. Oh, plus cxy will cancel out, so it's just px. Now, since this, okay, I have already, no, I have not used the fact that it is. What do I want to show? I want to show this property basically because it's some edge in the graph. I want to show that it has this property that p prime x plus cxy minus py is greater than or equal to 0 minus p prime y, right? So, okay, let's write. So, if I add, okay, so p prime x plus cxy minus p prime y, and what is p prime y? I'm just going to subtract p prime y, dsy plus px minus p prime y by definition is py minus dsy. Correct. So, dsy cancels and it's px minus py. Now, let's do it slowly. I want to prove these three conditions, or in particular these two conditions. Anything in the new matching, I want to argue that it is exactly this. And for every other edge, it has this greater than or equal to 0. The way I just update my p value by the length of the shortest path and its original p value. By magic, I have the compatibility conditions between the new matching and the new p prime are satisfied.
Also getting the same thing case PSP. Oh, you are doing the for the second thing, right?
Yeah.
So I'm also getting the same thing. It's boiling down to px minus py, but px minus.
Wait, I'm probably doing it on the residual path anyway, so that's what I should use. Not cxy, but the reduced cost. Okay, let's. So I have starting MP is clear. My whole algorithm is clear. Now I want to just show that.
What we need to show that the second condition is fulfilled for p prime.
Yeah.
Yeah. So as x is in some matching, so sx path is not.
So what did I want to share? So for, I think these three conditions is what I remember. I need to xy is in matching. 2 is that xy is in the new matching, but not in the original matching, and okay, for a matching, if it's in M prime, but not in the original matching. Let's see. These are three conditions I want to verify because anything in M prime, I have a stricter condition I want to satisfy. Yeah, m prime minus m and the remaining. And the remaining is okay, it could be also in m prime intersection m. No, if it's if it is in m, I have dealt with it. Okay, if it's part of m prime, I have to be careful because I have a stricter condition if it's part of m prime. Okay, so let's look at xy is in m. If xy is in m, then what I said is that I have this edge in gm. So what I know is that the length of the shortest path from S to X is length of the shortest path from S to Y minus C of xy. Now, should I do C of xy or C of reduced xy is another point. I think if I just assume it's reduced, then it's, yeah, let's do it in the reduced. Yeah, I'm going to do it only in the reduced world, which is Cp of xy. Because we argued that finding shortest paths in the original cost or the, okay, at least for cycles I argued. For paths you need to do a little bit more, okay, but that's, I'll come back to that. So we're going to do it in the reduced cost on the edges, yes, because they are the ones which are greater than or equal to 0, and I said you can apply Dijkstra and all that. So I think that was the problem I was struggling with. Now I think should be fine.
So it was px minus py, and over here we get minus px.
So which means what? So this is equal to d of sy minus px minus cxy plus py.
This boils down to whatever you were doing.
So this px I added here, right? So this is what, this is my p prime x is equal to, this is my p prime y minus cxy, and that's what I wanted. For every edge in M, I want this to be greater than or equal to 0, but I have something stronger in fact. P prime x plus cxy is equal to p prime y. So for any edge in the original matching, I actually have the equality satisfied, which is good. I really want it only for any edge in M prime, but I have it for any edge in M. Okay, so let's see if anything in M prime but not in M. Okay, if I have an edge which is in M prime but not in M, then how did it get into M prime? It has a similar thing, right? That means that yx was in the augmenting path. In the shortest augmenting path, I augmented by the shortest min cost path. In that min cost path, yx is there. That's why this edge xy got in, right? Because anything this was in M prime but not in M, because that means in the augmenting path this edge was there. So this was in the shortest augmenting path. So I have the same thing which is there, that dsx is equal to dsy minus cxy, and the whole thing is true. So it is true that I have it for that as well, because this is in shortest min cost augmenting path. Okay, now let's look at all other edges which are not in M prime or in M. That means they did not come to, so the proofs of these two are precisely the same, more or less the same. In the first case, we use the fact that this is the only edge coming into X in the residual network if XY is in the matching. And in the second case, we say that this edge is part of the shortest path augmentation. That's why it got into the new matching now. In the third case, for every other edge, it did not make it to M prime, means that it is not part of the augmenting path at all. So, dsy is less than or equal to dsx plus cxy in the residual, in the reduced path. What does that mean? Which means that this is px minus py would come. So p prime y is less than or equal to p prime x plus cxy, which is what I wanted. I want p prime x plus cxy minus p prime y greater than or equal to 0. I mean, this is because, I mean, since xy is not in M, this edge would be in the residual network. Since xy is not in M, this would be in the residual network. So, the shortest path from S to Y is less than or equal to shortest path from S to X plus cxy, simply by the property of the shortest paths. Okay, so all this imply that P prime and M prime are compatible. Okay, what does compatible means? That this is what I mean by P and M are compatible. And why did we want this? This means that G M prime has no negative weights, because all the residual, I mean, all the reduced cost edges, the reduced cost of every edge in the residual network is greater than or equal to 0, and that's it. So, this algorithm, so what is the overall running time of this algorithm? We are doing n augmentations, and in each augmentation you are doing Dijkstra's algorithm to find the shortest path from S to T, and along the way S to every vertex. And so that's like, Dijkstra will take you m log n. So, some low polynomial time, what we can do is minimum cost perfect match. Okay, so next week when I talk about linear programming, I'll come back and we'll discuss about this primal dual algorithms, and this is one example of modifying primal. In our case, the primal would be the matching, and dual would be some LP on the vertices, and so we are updating this dual variables and maintaining optimality in some sense. And when the primal and dual reach feasibility, then we got optimality. And later on, towards the end, when we will look at approximation algorithms, this algorithm is used for some TSP problem, okay? Minimum weight cost perfect matching. Okay.